Welcome learners, I am Sandeep Grover, Professor in the Department of Mechanical Engineering. So today in this session, we will learn about the transportation problems in the operational research. So this will be the lecture plan for the today. We will see that what is a transportation problem with the help of an example, why it is important, what are the different types of transportation problem, and what are the various methods for solving the transportation problem, that is the northwest corner rule, row minimum method, column minimum method, matrix minimum method, and the Vogel's approximate method. So let us go. Now a transportation problem is a special type of linear programming problem in operational research. You know, in operational research, we are concerned about the optimization. Optimization could be maximization of the problem, it could be minimization of the cost or minimization of the time. So it is a special type of linear programming problem in which items are carried from a set of sources to a set of destination based on the constraint that there are different supplies and demand for the resources or for the warehouses, and the purpose here is to transfer those units from the supply to the warehouses in such a way that the conditions or the constraints are also met and the total cost of transportation is minimized. So for example, this is the demand, and accordingly this is the your supply which is going on. There are constraints in the term that this is a limited supply in this case, and even the demand is limited. Based on these constraints, you have to transfer the units from this particular cell, that is a supply, to the demand in such a way that the total cost of transportation is minimized, and these are the cost of transportation that are given in the matrix. Let us see this with the help of an example. Say for example, there are three sources or there are three origins in this case, and equally are the number of the warehouses. Now each origin has a capacity. Say for example, the plant number 1 or the origin number 1, it has a capacity of say 24 units to manufacture. Plant number 2 has a capacity of 32 units, and accordingly these are the capacity of the warehouses. That means if you want to transfer number of units from say for example origin number 2 to the warehouse number 3, so you have to see that this is the capacity of the origin and this is the capacity of the warehouses. That means you cannot transfer more than 27 units in this case, and accordingly figures in this matrix, they indicate the cost of transportation. That means if you want to transfer a single unit from origin number 1 to say warehouse number 2, then the cost of transportation is ₹8 per unit. So if you transfer a single unit, you will have to spend ₹8. So accordingly these cost is given. Now you have to work out in such a way that the total cost of transportation is minimized. This is the transportation problem. Another thing, you see that the total of the all the say capacity of the supply or the origin and the capacity of the warehouses is same as in this case 94, but it could be different also. We will see that. So accordingly there are two types of transportation problems. One is a balanced transportation problem and one is an unbalanced transportation problem. So a balanced transportation problem is one that we have seen previously, that the capacity of the warehouse, capacity of the origins or capacity of the plants, which is 94 in this case, total capacity, this is equal to the capacity of the warehouses, which is again 94. These capacities are equal, so that means all the units over here can be adjusted in all these cells. Whereas the unbalanced problem is one where these two capacity is not equal. Maybe the say capacity of these plants in the origin could be say 100, and this could be say again 94. So then there is a gap of 6 units. That means out of the 100 units being produced in this plant, in these plants, you can only transfer 94. So 6 will remain. So this is called a unbalanced transportation problem. Now in the case of a unbalanced transportation also, where the supply and demand are not equal, you can always add a dummy row or a dummy column, okay, depending on the necessity, and then you can always make it a balanced problem. So you can create an additional row or you can create an additional column, and so that will be a dummy row or column, which means the cost of transportation in that case will be 0, and accordingly the units that are required from supply or demand can be put in, and then you can take up that problem, you can address that problem as you are addressing a balanced problem. Why? Because now you have converted that unbalanced problem into a balanced problem, fine. Now see, in a transportation problem, this is a case of minimization, that means overall cost of transportation has to be minimized. So first we have these 5 methods of solving transportation problem, which are also known as initial basic feasible solution. So you will see IBFS, these are these 5 methods: the northwest corner rule, the row minimum method, the column minimum method, the matrix minimum method, and the Vogel's approximate method. So that means initial basic feasible solution means all these are giving you some solution, that is a initial solution, and you do not know whether that solution is an optimal solution or not. So that means each of these solutions will be giving you a total transportation cost, and then that is not the end of the problem. You need to check up that whether that initial transportation cost that it is giving you, whether it is optimal or not. So one way is you can compare these cost by all these 5 methods and then see which is minimum one and go for checking the optimality. The other way is you can take up any of these methods, okay, solve the problem, find the solution, find the transportation cost, and then check it for the optimality. If it is optimal, then it is okay, then it is a solution. If it is not optimal, then convert that non-optimal solution to the optimal solution, okay. So let us see these say solutions one by one. Now this is the problem that we have taken to solve. This is one problem which will be solved by all these 5 methods, so that we can compare the results. You see, this is a source or a region, or you call it a plant which is manufacturing. There are 3 plants which are manufacturing certain units. So plant 1 is manufacturing 24 units, plant 2 32, and plant 3 is 38 units. So this is a demand or a warehouse. So in warehouses, these numbers of units can be kept. So that means warehouse number 2 has a capacity of only to keep 27 units. So accordingly, you see these are equal, and now we have to solve it by, say, first is northwest corner rule. Now in the northwest corner rule, as the name suggests, northwest. So that means northwest side, that is the upper left corner, you allocate the units as many you can, as many units you can allot, you allot over there, and then this will create another matrix, because when you allot all these units in the northwest say cell, either the capacity of the say the plant will be exhausted or the capacity of the warehouse will be exhausted. So this will give you a new matrix. So in that new matrix, again you follow the same rule, take up the upper left corner and then allocate, and then over the iterations you will find that all the allocations have been done. Now this method completely ignores the minimum transportation cost. So you should not, the probability of getting an optimal solution through this method is quite less. So this is what I have told you. So when you allocate like this, then you find out the total transportation cost. So now what I will do is I will take up the same problem, so that we saw in the slide number 8, and let us solve this problem. Okay. So northwest corner rule, we said that we take the northwest or the upper left. So upper left is this, where the cost of transportation is 7. So how many units you can allocate here? This origin is 24 capacity, this is 30. So you cannot allocate more than the capacity of the say origin in this case. So you can transfer 24 units in this case to this cell. So when you allocate 24 units over here, you see the plant number 1 or the origin number 1 capacity is now exhausted. So there are no units left in the plant number 1 to be transferred. So I put a cross for this like this. Okay. So when 24 units are transferred here, how many are remaining here? 6 units are remaining. So, that means the capacity of the warehouse 6 units it can accommodate more. Now, you see the first row can now be eliminated. Why? Because this is now over. So, if I eliminate it, let us say just like this. So, you see now you are with the new matrix where the uppermost side is this one. So, how many units you can allocate here? 32 is the capacity of the region, whereas 6 is the capacity of warehouse. So, you cannot allocate more than the capacity of warehouse. So, you can allocate here the say 6 units. So, when you allocate here 6 units, the capacity of warehouse is again now exhausted. So, I can put a line over this over, and over this. So, there are 26 which are still left to be allotted in the from the plant number 2. Okay. So, since this is exhausted now, so now I put a cross for this. So, now this is again given me new matrix. Okay. So, again going towards the northwest side. So, you find here how many you can allocate here? 26 are left here, 37 is the capacity. So, you can allocate here not more than 26. So, when you allocate here 26, how many are now remaining? You are left with the 11 units. Fine. So, now this is over. So, I can put a cross for this, because now this capacity of origin is over. So, you are left with this only now 8 and 2. So, directly 11 units can be plotted here and 27 units can be plotted here, that is all. So, this 11 is over, 27 is over, this capacity over. So, now this is the solution. 24 units are to be transferred from origin number 1 to warehouse number 1, 6 units to be transferred from origin number 2 to warehouse number 2, okay. 26 from this 2 to 2, 11 units from origin number 3 to warehouse number 2, and 27 units from origin number 3 to the warehouse number 3. So, what is the total transportation cost? 24 into 7 plus 6 into 8, and likewise. So, this solution I have tried to show you like this also. Okay. So, this is a solution that we have just solved this problem. This is the solution. So, this is the same matrix which we have solved, and the total transportation cost is 487. Now, you have no idea whether this 487 is optimal or not. You are just working on the initial basic feasible solution. So, this one of the methods, northwest corner rule, has given me a solution of 487. Okay. Now, I move on to the next method, which is the row minimum method. Now, in row minimum method, as the name suggests, it is the minimum number in each row or the minimum cost in each row that is to be taken first. So, the allocations are made starting from first row in the cell where the cost is the minimum. After allocation in first row, move to the subsequent row, that means first to finish with the allocations in the first row as per the cost, and then you move on to subsequent rows to make further allocations as per the row minimum method, and then again find out the total transportation cost that as we have calculated earlier. Okay. So, let us again solve this problem, row minimum method. Okay. Yeah. So, row minimum, take up the first row, see the minimum cost. The minimum cost is 3 here. So, how many units can be allotted here? Since 24 is the capacity of warehouse, capacity of the plant or the region, 37 is the capacity of the warehouse. So, you cannot allot more than 24 units here, because it is only 24 that is available and to be transferred. So, this is the 24 units that are transferred. Now, once you transfer 24 units from say origin number 1 to the warehouse number 2, the capacity of origin number 1 is over now, okay, and here you are left with the capacity of 13. Fine. Again, once the say capacity of this origin or the say plant is over, in order to avoid any confusion, we say that this you can take away, and now you are left with the second and the third row. So, when you move on to the second row, here you find the minimum cost is 2. Okay. So, how much you can allocate here? Since the capacity of this plant is 32 and the capacity of warehouse is 27. So, you cannot allocate more than the capacity of warehouse. So, 27 you can allocate here, fine. Once you allocated the 27 here, you are left with 5 here, and this is over. But row minimum method, this row is still left to be completely exhausted. So, I want to exhaust this row first. So, now I move on to the next higher cost. After 2 next higher cost is 6. So, I will see that how much can be allotted here. So, here I can allocate from the origin 5 is the capacity, and for the warehouse 13 is the capacity. So, minimum is 5 out of these 2. So, I can allocate 5 units here, fine. So, once I allocate 5 units, this is exhausted and you are left with 8 over here. So, that means row number 2 is again now over, fine. So, now as per the methodology of this row minimum method, we move on to the third row. Minimum cost is 2, okay, and it would have been best since it is a minimum cost in the complete matrix. But in this case, you find that the capacity of this warehouse is over. So, when the capacity of this warehouse is over, you cannot allot anything. So, now you need to move to next higher cost, which is 4 here. So, how much you can allocate here? 30 is the capacity of the warehouse and 30 is the capacity of origin. So, you cannot allocate more than 30 since it has a limited capacity. So, I can allot 30 units here. So, this is over, okay, and you are left with 30, sorry, you are left with the 8 units only, and then next higher cost is this, that is all. 8 units are left here. So, you can allot 8 units with this cost, fine. So, this completes, now this is also over. So, now this completes the allocation. So, as per row minimum method, 24 units are to be allotted, are to be transferred from origin number 1 to warehouse number 1, 5 units from origin number 2 to warehouse number 2, and 27 units from origin number 2 to the warehouse number 3, 30 units from origin number 3 to warehouse number 1, and 8 units from origin number 3 to the warehouse number 2. So, again I have shown this solution 24, sorry, yeah, okay. So, this is what we found by solving this problem. So, this is a solution, and the total cost of transportation is 340, okay. So, now you got 2 cost of transportation. So, let us compare them at the end, that which is the best one, fine. So, this is by the row minimum method. Now, let us move on to the third one, that is the column minimum method. So, as we were talking about the row, in the row minimum about the rows, so here we will talk about the column. So, in CMM the allocations are made starting from the first column where the cost is the minimum. So, the first column, see which is the minimum cost, make the maximum allocation that you can make here, and after allocation in the first column, move to the subsequent columns, next column, and then make further allocations based on the minimum cost in that particular column. So, once you exhaust the first column, then only you need to move to the second column, okay, and then accordingly find out the total transportation cost. So, let us see the same problem, okay. So, this is the problem, and let us solve it with the help of the column minimum method. So, we move to the first column. So, in the first column the minimum cost of transportation is 4. So, allocations can be done here, maximum allocation. The capacity of origin is 38 and capacity of this warehouse is 30. So, you cannot allot more than 30 based on the capacity of warehouses. So, this comes 30 over here, fine. So, when you do 30 over here, so you are left with 8 units in this, okay. So, now by chance in the first go only the capacity of this column number 1 or the warehouse number 1 is over. So, you can move on to the next column. So, when you move on to the next column, in this column you see the minimum cost is 3, okay. So, how many you can allocate maximum here? Seeing this 24 here and 37 here, origin capacity is 24, you can allocate maximum here 24. So, when you allocate here 24, this is over, this capacity is over, and here you are left with the 13 units, but still this capacity of warehouse is remaining. So, you move to you need to see that the next higher cost is 6. So, the maximum allocations that you can make here is 13. Okay. So, when you make allocation of 13, this is exhausted, okay, and here you are left with the 19 units, fine. So, now we move on to the third column, okay, and in this third column you see that the minimum cost is 2 in 2 cases, and there is no other option, both are in front of this minimum cost only. So, you allocate here 8 and you allocate here 90. So, this exhausts this also, and you are left with no units over here. Now, one thing you must see here, in case where this the cost minimum cost is same, then in the initial basic feasible solution, you try to allocate where you can put on the maximum number of units. So, if so by chance in this case both are allotted directly, but if given a choice you must allocate where maximum can be allotted in the minimum cost. The reason is this will bring you more near to the optimal solution. Anyway, if you do not do it like this way, but then you will have to do in the next iteration when you go for the converting the non-optimal solution to optimal solution, fine. So, this gives us a solution. So, you allocate it like this in the column minimum, and let us see that how much we are getting. Okay. So, this is what is the solution that we got by the column minimum method. 24 units from origin number 1 to warehouse number 2, 13 units from origin number 2 to warehouse number 2, 19 units from origin number 2 to warehouse number 3, and accordingly. And you find out the total, calculate the total cost of transportation, multiplying with the cost of transportation and the number of units that are allotted. So, 24 into 3 and so on. So, here you get the total cost is 316, fine. Okay. So, now let us move to the next method, that is the matrix minimum method. So, this is like a combination of both the row minimum and the column minimum, and the purpose here is that you find out what is the minimum cost in the total matrix, out of this cells, and then you start with the cell where a minimum cost is there in the entire matrix. So, after allocation in the cell, move on to the subsequent cell with the minimum cost to make further allocation. That means, you do not have to move in a row wise or a column wise, you see the overall picture of the matrix, and wherever is the minimum cost, you just start going from the minimum to the next higher cost. Okay. Do the allocations and then again find the total transportation cost. So, let us solve this problem. Fine. So, in this complete matrix, the minimum cost is 2. Okay. So, you can do allocation of 2 here also and 2 here also, but in both these cases, you can make the allocation since you can allocate only 27. Okay. So, let us start with this. When you allocate 27 units over here, so this 27 is exhausted, the warehouse number 3 is exhausted. In the plant number 2, you are left with a capacity of 5. Okay. Next higher cost. So, now in this 2 you cannot allocate any more because this is already exhausted. So, the next higher cost in this is 3. Okay. So, in this the maximum allocation can be done is 24, because the capacity of origin is 24 and you cannot allocate more than the capacity of warehouse, sorry, capacity of origin. So, here you are left with the 13 units, fine. Move on to the next higher cost, which is 4 over here. So, how much allocation you can make here? The capacity of origin is 38, okay, and the capacity of the warehouse is 30. So, maximum allocation that you can make here is 30. Okay. So, when you maximum allocation is 30 are exhausted here, the capacity of warehouse number 1 is over, and then you are left with the 8 units in origin number 3. So, let us move on to the next higher cost, which is 5, but you cannot make any allocation in 5 since 27 is already exhausted. Let us move to next higher cost, which is 6. So, in this you can make allocation of 5 units. So, when you make allocation of 5 units, this 5 goes away and you are left with the 8 units here, fine. So, what is the next higher cost? Next higher cost in this case is 7, You cannot make any allocation because the capacity of warehouse number 1 is already over. Fine. Next higher cost in this case is, this is 8, okay, and the next higher cost. So, here also you cannot make any allocation since this capacity of the region number 2 is over. So, only left choice is with us is this, where you can transfer the 8 units. Fine. So, 24, 5, 27, 38. So, this is what is the solution that we got through the matrix image method. So, let us see how much is the total transportation cost. Okay. So, this is what we calculated, okay, and in this case you will find that there may be a small variation in the solution by this method or with that method, because we got choices in this. So, the choice in this was available to this was that you could have allotted in one of the cells over here, and that is why you are getting this option. Fine. So, let us move on to the next case. Okay. Now, this is a Vogel's approximate method, which is VAM. Now, this VAM is basically a a different type of method which takes care of the penalties. So, you will find here that penalty is something which if you do not allot in the minimum cost, then where you will allocate. So, if you allocate to say in the minimum cost 2, okay, and the next higher cost is say 4 in a row or a column, so the penalty is going to become 2. So, you need to find out the penalties for each row and column by subtracting the lowest cost element in that row or column from the next lowest cost element in that row or the column. So, identify, so you will get penalties in all the rows and penalties in all the columns, that you will see. So, identify the largest penalty among the rows and columns, select the cell with the minimum cost in the identified row or column with the largest penalty. So, maximum penalty, minimum cost. So, wherever is the maximum penalty out of rows and columns, choose the minimum cost in that and make the allocation. So, when you make the allocation, this would create, this would give you a new matrix and then form the same rule in the next method. Okay. So, let us see this problem. Okay, sorry. Okay, so by mistake this is let me anyway, this is, we are just taking care of the seeing how the problem is solved. Yeah. So, this is considered as 1 in the original problem. So, let us take it 1 only, not 2. Anyway, it is methodology. So, penalty row wise and column wise. If I move on to the first row, the minimum cost is 3 and the next higher cost is 5. So, the penalty in this case is 2. Similarly, here the minimum cost is 2, next higher cost is 6. So, the penalty here is 4. Here the minimum cost is 1 and next higher cost is 4. So, the penalty here is 3. Okay. Similarly, if I move column wise, the penalty here is minimum is 4, next higher is 7. So, this is again 3. Similarly, in this case the penalty is 3 and in this case this penalty is 1 and 2. So, our rule was maximum penalty, minimum cost. So, let us see out of this these 6 penalties, maximum penalty is 4 and let us see minimum cost in this particular row, which is 2. So, now we need to target this one. So, I have to make maximum allocation 2, which are 27, because the capacity of warehouse is number 3 is 27 and capacity of this origin is 32. So, I can allocate 27 units. So, once I allocate 27, okay, this particular column is, I can delete it in a way that the capacity of warehouse number 3 is over. So, I just delete it like this. Okay. So, when I delete this column, now this has given me, okay, this will also now become 5. Okay. So, when I delete this column, this has given me a new matrix. So, for this matrix now I should apply the same methodology, find out the penalties. So, for this matrix, these will remain same because this all same. So, this penalty is 3, this penalty is again 3. So, these penalties are minimum into the next higher. So, the penalty in this case will be say 4, this case it will be 2 and in this case it will be 4. Okay. And in the second row these penalties I should again write, this remains same 3, 3 and 1. Okay. So, in this second iteration you see the maximum penalty is again 4. Okay. So, there are 2 4s in this. So, the minimum cost I need to see, minimum cost is 4 here in this row, whereas the minimum cost is 3 here. So, maximum penalty, minimum cost. So, now I need to target this particular cell where the cost is 3. So, I can make 24 allocations, fine, and when I make 24 allocations, I am left with 13 here. So, now this is over. When this is over, I can again delete this. So, now this has given me a new matrix. What is that new matrix? This is 2 by 2. So, here I see the maximum, the penalties, this is 2 here, same, and this again 4, that is same here. Okay. And in this case, the penalties will now change. So, this penalty will become now 4 and this penalty will now become 2, fine. So, maximum penalty, minimum cost. So, the maximum penalty in this case is again 4 out of this. Okay. The minimum cost is this 4 and here also if I come through row, here again the minimum cost is this. So, I need to target this particular cell. So, the maximum allocations that I can make here is 30, fine. So, this 30 is exhausted and I am left with the 8 units in this, fine. So, when this is exhausted, this again over. So, now I am left with nothing but these 2 cells only, okay, and 5 and 8 capacity, 13 is there. So, directly you can put in 5 units will come here and 8 units will come here. Okay. So, this is given me solution 30, 24, 5, 27, let us see. Okay, this is the solution that we got, fine. So, if there is some difference in the solution or in what we have depicted, it could be because we could have solved by another method. That means, we could have solved by any of these 5 methods, or maybe if the cost is same in 2 cells, then you have an option, you can allocate in any one of them first. So, with these numbers, this is what is solution that you are getting by VAM. So, the total cost of transportation will be calculated based on this. You can transfer 24 units from source number 1 to warehouse number 2, 5 units from origin number 2 to warehouse number 2, 27 units from this origin to number 3 and accordingly this one. So, if you see, you find the total cost of transportation by the same methodology is 340. Okay. So, now we have found the initial basic feasible solution by all the 5 methods, and these 5 methods are giving me this cost. So, if you recall, with the northwest corner rule, I got a cost of rupees 487, by row minimum method 340, by column minimum method 316, matrix minimum method 373 and Vogel's approximate method 340. Now, if I see all this, one thing is sure that this is the best cost out of this, out of these only. So, if I want to actually check up my solution, I should take up the allocations by this method, that is the column minimum method in this case, and then check up with the test for the optimality whether that solution is optimal or not. If it is optimal, it is well and good. If it is not optimal, I need to convert that. So, for checking the optimality, I can directly go here, or if I just need to check my optimality, okay, I can also check any of these other methods for the optimal test, and I am sure that it will not be passed because these costs are already higher than the column minimum method. Okay. So, in this session, we have seen that what is the transportation problem, what are the types of transportation problem, and how the initial basic feasible solution can be found with all these 5 initial basic solution methods. And then in the next sessions, we will see that how to check on the optimality and how to inference that whether this is optimal or not, and how to convert the non-optimal solution to the optimal position. Okay, so this is over for now. So, thank you.